whenever I talk about current, what would you have in mind? You would say that current is basically the flow of charge. This is a circuit. You can clearly see there is a battery. There are two plates of the capacitor connected with the battery. What do you think will happen when the needle of the compass is, let's say, here? Now we will start calling it as conduction current. You can write the four equations of electromagnetism just for the sake of doing it. Hello students, welcome in today's class. In today's class, we are going to talk about displacement current. Alright, so before we even start with this topic, whenever I talk about current, what would you have in mind? You would say that current is basically the flow of charge, or there is a net flow of charge. That is how you look at current. But after today's class, your perspective of looking at current will completely change, hopefully, and thanks to this gentleman, James Clerk Maxwell. All right, and also we'll talk about Ampere. We'll understand how these both gentlemen will contribute to this final theory of electromagnetism. All right, so before we start with that, let's take this as an example. So this is what Maxwell came up with. This is a circuit. You can clearly see there is a battery. There are two plates of the capacitor connected with the battery. All right, so now let's think of it like this. T is equals to 0, the switch is closed. All right, T is equals to 0, the switch is closed. What do you think will happen? You will say a current will start flowing in the circuit. A current will start flowing in the circuit. So there will be a building up of current. While that is happening, the charge is building up here. All right, so let's say there is a charge plus Q depositing on this plate, and similarly current is exiting out of this plate, and we can say an equal and opposite charge is accumulating on the second plate. This is something you know. That's because this is how a capacitor would behave. It starts charging. All right. Now, James Clerk Maxwell, what did he think? He thought about, having a current in the circuit here. Of course, there is a current. And there is also an associated magnetic field. So he bought a compass here, a magnetic compass, and when he switched on the circuit, the compass showed some deflection, which was very obvious because initially the current is flowing and the capacitor is charging. This is what you know because of your previous classes. Now, what do you think will happen when the needle of the compass is, let's say, here, somewhere in between the plates? So as you know from the theory of capacitor, that charge is accumulating here, let's say positive charge, and equal negative charge is accumulating here, and that is why the current is exiting like this. But there is no flow of charge between the plates of the capacitor. Either there is air or there is a dielectric. You cannot expect current to flow in between the plates of the capacitor. So the magnetic needle should not show any deflection. That's because there is no current here in between the two plates. But surprisingly, the needle did show some deflection when the switch was just closed, indicating what? That without a current, you are seeing a magnetic field now. What are you seeing? You are seeing a magnetic field without a current. But that existed only till the current was there in the circuit. Do you know this? That current is in the circuit only till steady state is achieved. Only till steady state. Now, what do you mean by steady state? Let's look at it again. So let's say this is hypothetically a battery of 10 volt and this is a capacitor of 2 microfarad. Then what is the last charge it can take? So you would say Q is equals to CV, and C is 2 microfarad and V is like 10 volt. So this is going to be 20 microcoulomb. Beyond 20 microcoulomb, this capacitor cannot take further charge from this particular battery. And then you would say that current has become 0. Steady state is achieved and current has become 0. And then the needle here, which I had placed here, will also stop showing any deflection. That is why I said that there is only an initial deflection. All right. So now you understand the behavior of this whole circuit when there is a capacitor and there is a battery. But the question still remains unanswered, that how did the magnetic needle show deflection in between the plates of the capacitor when there was No current, because if you talk about Ampere, he gave a law which is called the Ampere-Circuital law. What is that law? Integration of B dot dl is mu naught times I enclosed. So you can only expect a magnetic field when there is a flow of charge. When there is a flow of charge. Even in magnetic material, there is flow of charge that creates a magnetic field. Is that fine? So you cannot expect a magnetic field when there is no current. So look at it like this. Let's imagine that there are, let's say, two different Amperian loops that we are talking about. Let's say this is one loop which I have made, let's say L1, and this is the other loop, let's say L2. So can you imagine again, there are two loops, L1 and L2. One is just to the left of the left plate and the other is just to the right of it. And if we try to apply this Ampere-Circuital law for the two, alright, so integration of B dot dl is mu naught times I enclosed. Alright, so I can write this as I, let's say. The current flowing in the circuit is, let's say, I. So I will remove this and I will write that this is I. I have written this for loop L1 and only for the time when there is the transient state. So steady state is not yet achieved. Okay. So there is current in this circuit, even though for some few milliseconds, but there is a current. Imagine if you write this for L2, then it should be 0. Why? Because there is no current. Current is only till here. After the capacitor, there is no current. So what will you say? What will you say? Obviously, this is what Maxwell said, that it looks like there is some inconsistency in the Ampere-Circuital law, because even the experiments were supporting him. There was a magnetic field here. The magnetic needle was showing some deflection here, but there was no magnetic deflection in between the. So, but there should be no magnetic needle deflection in between the plates, but there was actually. So, you know, there is a problem. Somehow we cannot assume that Ampere-Circuital law has accommodated the entire theory of it. There is some problem in this. What can we think here? What can be the possible reason for a magnetic field without having a current? This is what Maxwell said. So look at it like this. You know that electric field and magnetic field are not completely different from each other. They have an a connection somewhere. Thanks to Faraday's law, where he suggested that a change in magnetic field produces electric field. That is what Faraday's law is. That whenever you change magnetic field, you change magnetic flux. There is a current induced, there is an EMF induced, there is an electric field induced. So somehow a change in magnetic field produces electric field. Maxwell said that look at it like this. When there is current in the circuit, what is happening? When there is current in the circuit, what is happening? There is a building up of charge. There is a building up of charge. Alright. And when there is a building up of charge, there is a changing electric field. There is a changing, can I write it like that? So there is a changing electric field. So this must be producing the magnetic field, because once the steady state is achieved, this current will become 0 and the changing electric field will also not be there. That is, electric field will become static. So now to accommodate that, let's again take this example. Let's again have this diagram. So think of it like this. What is this current? Now we will start calling it as conduction current. We will start calling it as conduction current. That is the conventional current, you can call it like that, which is equal to what? dq by dt, which is nothing but dq by dt, rate of change of charge. Now look at it like this. So if this is dq by dt, and if you know the basic theory of it, that electric field is sigma by epsilon naught between the plates of a capacitor. Alright, it is sigma by epsilon naught. Okay, where you can write sigma as q by a, isn't it? You can write sigma as q by a, where sigma means the surface charge density very quickly. All right. So can I replace q by sigma into EA? You would say, of course, yes. Let's do that here. Okay. So current will now be dq by dt. Current is dq by dt, but instead of q, what I'm writing is epsilon naught into EA. Would you like to call EA something else? Of course, E into A is the flux. So can we say I is equals to electric flux, rate of change of electric flux, okay, with respect to time? Can we call this as an equivalent term to current? Of course we can. That is what he did. He called this as the displacement current. What did he call this? Now you might be wondering, what is the word displacement here? What is being displaced? Charge is not moving at all. But if you understand the field lines, so when the field is changing, the field lines are moving, and if the field lines are moving, they are being displaced. That is why we use the term displacement current. So whenever there is a movement of electric field lines, we associate displacement current, we associate this thing over there. Then Maxwell said, therefore you need to modify Ampere's law in the first place, and he started calling it the Ampere's-Maxwell's law. Obviously he will also take some credit, and he started calling it Ampere's-Maxwell's law. What is it? Integration of B dot dl, that is the line integral of magnetic field, which you know is going to be mu naught times of I plus ID, or IC plus ID. So he said that let's not modify Ampere's law, let's have it as it is, but let's make let's not discard Ampere's law in a way, and let's just make a small amendment to it. All right, now this law looks complete. Let's understand how. Again, let's have those loops over here. Let's say this was loop L1 and this is, let's say, loop L2. All right, so what would you write now? Integration of B dot dl for L1 is going to be mu naught times. So what do you have in case of L1? You have the conventional current, but you don't have any field lines, electric field lines. So this term is I, but this term is 0. So this term is I, this term is 0. Looks complete. That is all right. Now let's talk about L2. So when we write L2, this is going to be mu naught. Do we have conventional current here in L2? The answer is no. There is dielectric, there is no current. So can we call it 0? But do we have displacement current here? Of course we have, because the electric field lines are changing. So now this is I plus 0, this is 0 plus I, but now the law looks complete, and that justifies that if there is a magnetic needle here, even that should show deflection, and if there is a magnetic field here, then even that should show deflection. So there is a magnetic field associated with a changing electric flux, just like Faraday suggested that there is an electric field induced whenever there is a changing magnetic flux. Can we say that now, as nature loves symmetry, this law has become complete? A changing electric field produces magnetic field, a changing magnetic field produces electric field. In fact, that is how you were, or in fact scientists were able to justify the existence of electromagnetic waves, that how electromagnetic waves function, how they propagate even when there is no medium. They can even propagate in vacuum. How is that possible? We'll talk about that. All right, we'll talk about that. But before that, if now someone asks you, what do you mean by displacement current? So keep three things in mind. First, it is not current in the conventional form that you normally think of. It is basically a term equivalent to current. It is a term equivalent to current which you will associate whenever there is a changing electric flux, all right, or the displacement of electric field lines. Hence the name displacement current. All right. Next thing, because of this addition of displacement current, the law now became complete, and we could justify that it's not only moving charge that produces magnetic field, even a changing electric flux produces magnetic field. All right. And the third term, in situation like this, it is very evident that here if we have conduction current, then we don't have displacement current. Here if we have displacement current, then we don't have conduction current. All right. So this is how, you know, the this law was given, the Ampere-Maxwell's law, and it eventually, you know, gave the complete 4 equations of electromagnetism. So we sometimes call them the 4 equations of electromagnetism. But before that, I was talking about how electromagnetic waves move. So it is just like, you know, there is an oscillating charge. Imagine like that. On the sun, there is an oscillating charge. So it will produce a changing electric field. Of course it will, because it's oscillating. So its electric field is dynamic. That changing electric field produces a changing magnetic field. Who suggested that? Maxwell. Now it looks complete. That changing magnetic field then again produces an electric field, and then again, and then again. So this creates a domino effect, and even without a charge moving, its electromagnetic disturbance can propagate to thousands and thousands and light years of light years without any hindrance. So this is in a way very fascinating, and now you can understand what exactly, you know, can be a wave which can even travel without medium particles, because we could never think of it like that, because waves were always believed to travel with the help of medium particles, but here it is traveling without medium particles. All right. So displacement current, are you able to understand? You want to write one line definition, you may write that it is the term equivalent to current that can produce that can produce magnetic field due to change in electric flux or displacement of electric field lines. And how easily he got to this value? How? Just by, you know, equating the conduction current to displacement current. So IC is dq by dt, that is, and q we wrote epsilon naught EA. Of course, that means we are writing it in vacuum. If it is some other medium, then it has to be epsilon. It cannot be epsilon naught. Then the permittivity of the medium has to be taken into account. All right. So that's about displacement current. I can write the 4 equations of electromagnetism just for the sake of doing it. So integration of E dot dA, all right, is Q enclosed over epsilon naught, or sigma Q enclosed over epsilon naught. This is called the Gauss law. All right. In electricity, you can call it Gauss law in electricity. All right. What is the next? So let's say the next one is Gauss law in magnetism. B dot dA, the surface integral B dot dA or B dot ds, whatever you wish to write, is equals to 0. What is Gauss law in magnetism? Of course it is 0. Magnetic monopoles do not exist. So this is called Gauss law in magnetism. All right. The third is the Faraday's law. So I am in a way, you know, giving a farewell to the entire electromagnetism by giving these 4 equations. All right. So let me choose this color. All right. So this is the Faraday's law. What is the Faraday's law? So you would write E dot dl, E dot dl, that is EMF, is equals to minus d phi b by dt, or negative of rate of change of magnetic flux. This is called the Faraday's law. All right. And the last one now, which we have just learned today, so it is with a slight modification, of course, is called the Ampere-Maxwell's law. All right. So what is that? Integration of B dot dl, that is the line integral, is equals to mu naught times I plus epsilon naught d phi E by dt, that is the rate of change of electric flux. That's called the Ampere-Maxwell's law. So these are called the 4 equations of electromagnetism. All right. So I have talked about what displacement current is, and in a way how it is justifying how electromagnetic waves propagate. Somehow I have this feedback all the time that students are unable to understand displacement current very easily, or they have a problem in understanding that. That's probably because, you know, your mindset of looking at current is when you see a charge moving or flowing, but here you have to imagine a current like quantity even when there is no charge. Probably that's the root cause of the problem. So you don't take it like current in the conventional form, but you take it as a term equivalent to current, again capable of producing magnetic field. So I hope you were able to understand how Maxwell contributed to this and ultimately explaining the whole existence of electromagnetic waves. But that's all for this particular class. We will keep coming up with such videos where we will discuss those topics which normally would bother a student. But that's all for this. I hope you were able to learn. Bye bye. Thank you. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.